guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we move on to talking about acids and bases. So we all know that biological systems are very sensitive to pH. And so this is a pH scale of some everyday items where highly acidic is in your stomach acid. We have lemons, grapes, tomatoes that are more on the acidic side. And then in the neutral, we have pure water. And then we have some other items that are bases. And so let's start out by talking about acids. Acids have sharp, sour tastes, such as vinegar containing acetic acid, which you guys should be familiar of. And the reason why it's an acid is because it loses a proton, or H+. So acid loses H+, and water picks up the H+ to form a hydronium ion. So when this is picked up by water, it creates a hydronium ion, H3O+. And an example of an acid reaction is HCl, which is a very strong acid, combined with water, which is a liquid, and then getting this hydronium ion, which we just talked about, which is aqueous, and Cl-, which is aqueous. So acids are proton donors. Proton donors, and are called Bronsted acids. And then we can also look at it in terms of being an electron acceptor. Which makes it a Lewis acid. So basically there's these different definitions of what kind of acid it can be, and based upon whether it's a Lewis acid, it's an electron acceptor. If it's a Bronsted acid, it is a proton donor. So both types of acid result in another species becoming more positively charged. So both result in something being positive. So there's a lot of different Bronsted acids. Examples of that I can draw right here. The most common one is HCl, or hydrochloric acid, hydrogen bromide, HBr, also known as hydrobromic acid, nitric acid, HNO3, carbonic acid, H2CO3, sulfuric acid, H2SO4, and there's also things like benzoic acid, which is a weak acid, C6H5COOH, but this guy is weak. So the reason why I wanted to write this out for you is because it's obvious why all of these acids are proton donors. They have this H+ that's present that can be donated. So the common organic acid group is the carboxyl group. And the carboxyl group is COOH, and this is often found in biological molecules. So to show you guys how the organic molecule looks, we have C double bonded to an O, and then OH, whatever this is just an R group. And this goes to COO-, and a release in a proton. So strong acids produce more protons in solutions than a weak acid. And so let me draw that up right here. If we start out with something with a proton attached to it, for example, HCl, HBr, whatever it is, and then it dissociates into A- and a proton, H+, remember we talked about equilibrium constants in the chapter before, and we can write this as the product over the reactant. So a strong acid produces more protons in solution because it dissociates more. So strong acids are almost completely ionized in solution. On the other hand, weak acids are incompletely ionized in solution. So what that means is that for a strong acid, this AH, whether it's HCl, HBr, completely dissociates into its ions. And since it's completely dissociating, that means we have a higher concentration of the H+, meaning that it's a strong acid. Now let's talk about bases.